In this lesson, we're now going to look at what happens in detail as the current begins to flow through an inductor. Now, from our last lesson, we know the endpoints. So at time t equals 0, we get a maximum rate of change of flux through the inductor. The induced EMF spikes, shuts off the current. At time t equals infinity, we're going to reach a steady state value where the current is going to settle into its final value. Based on Ohm's law, the current will be, maximum current will be the battery voltage divided by the resistance. Well, we're going to follow the same type of analysis that we used for the RC circuit. We're now filling in the middle between the endpoints, and we are going to use a Kirchhoff voltage loop equation to set up our differential equation. So our Kirchhoff voltage loop equation is going to be just the one loop, one perimeter equation. So there's our Kirchhoff voltage loop. We have the battery voltage, which is our EMF here. Now the inductor acts as a voltage source because it's an induced voltage. And notice it will impede, so that's why the negative is in here, impede what the battery is trying to do, and that equals the sum of the voltage drops, the IR. So we have simply done algebra to go from this step to this step. So divided out the L, so we have di dt plus I times R on L equals battery voltage over L. So please make sure you see how the algebra makes sense, because that is going to be our first order di dt, right? So just first derivative, first order differential equation that we are going to solve it by separation of variables, and conceptually identically to what we did for the RC circuit. And we're going to see a very familiar result. So let's get right to that and go to our next page. So I've simply rewritten the differential equation here. And to me, the trick to getting into this derivation, this solution to the differential equation, to derive the current as a function of time as it flows in the RL branch of a circuit, is to remember that we are going to isolate the di dt and do no more algebra with the rest of the variables. We're just going to bracket them together. So bracket everything together, just get the di dt by itself, and then it is a u sub. So that's the only parts I memorize, right? I don't memorize the Kirchhoff voltage loop. My memorization in terms of getting into this solution is that I have to get di dt by itself, bracket off all the other variables, and then it becomes a u sub. So the u substitution is the bracketed term that we bracketed off, so that's our u variable. And hopefully you remember this from calculus. Du di will equal negative r on L, so bring up the di, so du equals negative r on L di. And we almost have what we need, but we are missing the negative r on L. So we put it into our integral, and we factor out L on R to make it negative L on R, because you can always multiply by 1. Notice our limits of integration go from 0 to t, not to infinity. So we don't go to the endpoints because we're interested in a solution in between 0 and infinity. So we only go to time t, and we're going to go to a generic current I. So I will be somewhere between 0 and I max based on Ohm's law. Well, when we integrate both sides, we have a 1 on u du is natural log of u. So there's our natural log of u. We're going to evaluate it final minus initial. So that's why we have our final minus initial. And then it's natural log of A on natural log of B to go from this step to this step. So property of logs. We have our time constant. So now L on R, right? Henries divided by ohms is a second. So we're going to make sense of the time constant in a very similar way as we did to the RC circuit. And the rest is algebra. So once we have our natural log of A on natural log of B, natural log is a base E, so we let E operate on both to get rid of the ln, and we get E minus Ri. You can see we lose the L's above, so make sure you have all your algebraic steps in here, please. The L's go away, and we then do our final algebra to isolate the current as a function of time. And as I said, we get a very familiar mathematical structure in our result. Notice we have the amplitude, the maximum current, is going to be based on Ohm's law, battery voltage divided by the resistor that's in series with it. The bracketed term will go from 0 to 1, so that will represent our percent, right? So that's going to equal our decimal percent. Decimal percent to I max. And we are going to look at the equations and the time constant and take a look at the RL circuit in more detail mathematically in our next lesson. But you are responsible for this derivation. It is not a very long or complicated derivation. As I said, my memory, what I try to memorize to get into it is isolate the di dt, bracket off everything else, u sub. So please make sure you have your notes for this page annotated completely.